Hello and welcome to this video about earned value analysis. In the next few minutes, we will explore together, using a case study, how this method helps measure the success of a project, identify deviations early on, and make precise forecasts for project completion. The earned value analysis was developed in the 1960s and became a central tool for monitoring ambitious US space projects, particularly the Apollo moon landing. This method fundamentally changed project management by evaluating the value of work completed in relation to the costs incurred. At the start of the new millennium, the earned value analysis was enhanced with an important component known as the earned schedule. This extension includes not only costs, but also the time factor in the analysis, helping us assess progress against the original schedule. Are you ready to dive into earned value analysis with me and unlock the keys to successful project control? Then let's analyze the announced case study together. Please note that for the sake of simplicity, it is linear and idealized. In reality, projects are, of course, more complex. Imagine you have taken on the management of a project under the following conditions. The project budget, referred to as budget at completion, BAC, in the earned value analysis is £60,000. It is distributed across a total of 60 tasks, with each task budgeted at £1,000. The planned project duration, schedule at completion, SAC, is 8 months. We will enter this information into a coordinate system. The visual representation helps us understand the project development and identify deviations from the original plan. On the horizontal axis, time is plotted, representing our planned 8-month project duration, while the vertical axis shows the total budget of £60,000. If we connect the origin of the coordinate system with the point where budget and duration intersect, the resulting line represents the planned progress of work at a specific point in time within the project. This planned value, PV, is expressed in terms of cost, plotted along the cost axis. Let's now take a look at the project status after 5 months. We examine the actual time, AT, the time actually spent on project work, to assess the progress and costs. For this, we first calculate the planned progress of the work. This is done by dividing the budget by the project duration and then multiplying the result by the time spent so far. In our example, the planned value after 5 months is £37,500. However, the actual costs, AC, incurred so far already amount to £50,000. This indicates that the project is over budget. Our project team has successfully completed 30 tasks during this period, corresponding to an earned value, EV, of £30,000, 30 tasks at £1,000 each. If the earned value cannot be directly determined from measurable tasks, it can be calculated by multiplying the percentage of project progress, known as the completion rate or percent complete, by the total budget. To evaluate the time progress, the earned schedule, ES, we divide the earned value by the planned progress of the work and multiply the result by the time spent on project work so far. The time value of our project is 4 months as of the reporting date. This means that the earned value of £30,000 should have been achieved after 4 months if everything had gone according to plan. This shows that the project is not only over budget, but also behind schedule. The analysis conducted so far has provided us with initial information on the project's status after 5 months. In addition to the overall budget and project duration, we have looked at the planned value, actual costs, earned value, and earned schedule. In the next step, we will take a closer look at the discrepancies that are already apparent. Specifically, we want to determine which cost, time, and schedule variances can be identified as of the reporting date, and how the results can be interpreted. The cost variance, CV, indicates whether the project has been more or less costly than planned so far. It can be calculated by subtracting the actual costs from the earned value. A positive difference suggests that the work was completed more economically than expected, while a negative value points to higher costs. In our case, the cost variance is minus £20,000, representing a negative variance of approximately 67%. The time variance, TV, indicates whether the project is progressing faster or slower than planned. The time variance is calculated as the difference between the scheduled time and the time already spent on project work. A positive value means the project is being implemented faster than expected, while a negative value indicates delays. In our example, the time variance is minus 1 month, equivalent to a deviation of minus 25%. The schedule variance, SV, is also used for time assessment, but is measured in costs. It results from the difference between the actual and the planned value, EV minus PV. A positive result indicates a time buffer, while a negative result points to a delay. Our current schedule variance is minus £7,500 or minus 20%. Overall, all three metrics indicate potential challenges in project management, whether related to costs, the timeline, or overall progress. To assess the performance and efficiency of our project, we will next analyze the three performance indicators: cost, time, and schedule performance index. For this, we will use an alternative graphical representation. The Cost Performance Index, CPI, measures cost efficiency. It is calculated by dividing the earned value by the actual costs. A CPI of 1 indicates that the actual costs match the planned costs exactly, illustrated in the adjacent chart by the blue dots on the planning axis. A CPI greater than 1 shows that the cost performance is better than planned, meaning the project is being completed more cost-effectively. The green dots above the planning axis illustrate this. If the CPI is less than 1, represented by yellow dots for a minor deviation and red for a significant one, it indicates that the cost performance is worse than planned. In our project, the Cost Performance Index is 0.6. In simple terms, this means that for every pound invested, we have only generated 60 pence so far. The Time Performance Index, TPI, assesses the efficiency of the project's time progression. It is calculated by dividing the earned schedule by the actual time spent on the project. A TPI of 1 indicates that the time actually taken matches the planned time, illustrated in the adjacent graph by the blue dots on the planned axis. A TPI greater than 1 indicates that the project is progressing faster than planned. The green dots to the right of the planning axis illustrate this favorable outcome. A TPI less than 1, shown by yellow dots for minor time deviations and red dots for major ones, indicates inefficient time performance. In our example, the Time Performance Index is 0.8. This delay in project time could be due to unexpected issues, resource shortages, or supply chain delays. The time delay increases costs, disrupts activities, causes customer dissatisfaction, and damages reputation. The Schedule Performance Index, SPI, measures overall efficiency, but typically focuses on time. It is calculated as earned value divided by planned value, illustrating the project's progress compared to the original plan. A value above 1 indicates that the project is progressing faster than planned, possibly due to efficient resource utilization. In contrast, an SPI below 1 signals that the project is behind schedule. In such cases, additional measures, such as adding resources, are needed to bring the project back on track. In our example, the Schedule Performance Index is 0.8. After reviewing the current project status, the deviations encountered, and the performance indicators, one final important consideration remains. We want to examine how the future of our project will unfold. This consideration leads us to the metrics Time Estimate at Completion, TEAC, Estimated to Complete, ETC, and Estimated at Completion, EAC. Let's first ask ourselves when our project will be completed and what costs will be incurred if we continue working as we have been. To answer this question, we'll take another look at the original chart we used and extrapolate the lines of the earned value and actual costs to project future progress. This gives us the opportunity to determine when the earned value will reach the planned £60,000 and what the costs will be at that point. Our coordinate system shows that the 60 tasks will only be completed in 10 months, which represents our newly expected project duration, the time estimate at completion. To calculate this value, the planned project duration must be divided by the Schedule Performance Index. Here we find that the projected project costs at this point amount to £100,000. This value is the estimated at completion. It is calculated by dividing the total planned budget by the Cost Performance Index. By subtracting the actual costs to date from the expected total costs, we finally obtain the anticipated remaining costs until project completion, the estimated to completion. In our example, these amount to £50,000. Alternatively, the expected remaining costs can be calculated by subtracting the earned value from the planned total budget and dividing the result by the Cost Performance Index. The financial risk of this scenario can be quantified at £40,000. This amount represents the difference between the expected total costs and the planned budget. Finally, it remains to clarify how the forecast for the time estimate at completion, estimated to complete, and estimated at completion would look if the remaining work is carried out according to the original plan, but taking into account the deviations that have occurred so far. In this alternative approach, the lines for earned value and actual costs are not extended linearly, but run parallel to the planned value from the cutoff date onward. The calculation of the relevant metrics is then as follows. The expected total project duration is calculated by subtracting the identified time deviation from the scheduled total duration, SAC minus TV, resulting in a duration of 9 months. The costs until the project completion in this case result from the difference between the total budget and the earned value as of the reporting date, BAC minus EV. This calculation forecasts a required remaining amount of £30,000. To determine the total cost at the end of the project, estimate at completion, we subtract the identified cost variance from our total budget, BAC minus CV, which brings us to a result of £80,000. Both methods present different ways to predict the end of the project and the total costs. The choice between the two forecasting approaches essentially depends on which type of information and influences should be taken into account when predicting the project completion and overall costs. Another option could be to calculate an average of both results. Done. We have determined the key metrics of the earned value analysis. In doing so, we interpreted each value and clarified the significance of identified deviations. At the same time, we examined what forecasts could be made as of the reporting date regarding the project's completion. With this understanding, we can now effortlessly apply earned value analysis in the management of complex, non-linear projects. A well-structured Excel spreadsheet with correctly entered formulas or the use of a planning tool like Project Libre is sufficient for this purpose. After watching this video, interpreting the results should no longer be a challenge for you.